In this exercise, we have to plot these functions. These are functions that perhaps are a bit peculiar in the definition, right? So for instance, take the first one here is a function that is defined as the minimum of two functions. So we first have to plot these two and then compare them and take the minimum at every point, right? So we're going to plot them one by one, and we'll start with the first one here, right? The logarithm of the absolute value of x plus 3 is easy to plot, right? It's just the logarithm but shifted, okay? And of course copied because you have an absolute value. So you have here the vertical asymptote at the point -3, right? Where the logarithm is not defined, and then it looks what the logarithm looks something like this, right? So that's the logarithm of the absolute value of x plus 3. If you want to know what the point here is, well, this is when this is equal to 1, right? Which is, so x plus 3, well, actually, when it's equal to, yes, when it's equal to 1, right? So that means that x is equal to -2. So this point here, well, it's actually 2, perhaps 2 shifted to the right, but this point is -2. And the mirror image of this is -4. So this point here is -4, okay? Well, this is all that we have to know about this function here. Then we have this other function, right? Well, this other function is not defined when x cubed minus 3 is equal to 0, or x is equal to the cubic root of 3. Okay, that's the only point where it's not defined. All right. So it's got a vertical asymptote at that point, which is a positive point, and it's what the cubic root of 3 is 1 point something, whatever, right? So it's probably here, okay? So you have a vertical asymptote there. Well, actually, let me plot it here separately, right? So you have this point, okay? And you have a vertical asymptote at this point, right? And now we'll see what the function looks like around this asymptote. So we have the, let's say, f, well, not f, let me call it y. Y is the logarithm of the absolute value of x cubed minus 3, right? And if we take the derivative of this is equal to 3x squared over x cubed minus 3, right? And but this is the denominator here is negative to the left of this point and positive to the right of this point, okay? And this factor is positive. So the function is negative here, positive here, so it decreases in this region, increases in this region there. All right? We can calculate the second derivative just to see if there is a peculiarity in the concavity of this function. And well, this is 6x multiplied by x cubed minus 3 here, minus 3x squared multiplied by 3x squared, which is the square of this divided by x cubed minus 3 squared. So the denominator is irrelevant for sign. And here we have 6x4 minus 18x minus 9x4 over x cubed minus 3 squared. And then we have here 6 minus 9 is minus 3. So we have a global factor minus 3 minus 3x, right? That multiplies, here you have x cubed, okay? And here we have plus 3 is 6. 6, sorry, 6. That's it. right? Minus 3x times 6 is minus 18. Minus 3x cubed is minus 3x4, which is what is left once you simplify this. And subtract 6 minus 9 and you get 3, right? So this is what is in the numerator, okay? And down here you have x cubed minus 3 squared. All right, so you have here two factors, okay? And both of them change sign. So, well, you have peculiarities here. So the 2 points where this happens are 0, okay, the point here, actually the point here, 0, and another point on the left, which is the solution of the equation x cubed plus 6 equal to 0, or x equal to minus the cubic root of 6, all right? Remember, there's no problem with the sign of cubic roots, right? Because cubic root of a negative number is a negative number, okay? There's no problem in that. So this is a negative number and it will be somewhere, let's say here, minus 3, 6, right? So when we are here, both factors are negative, so the product is positive, and because of this minus sign, it's negative. So the function here, the second derivative is negative, so the function is concave. Here, one factor changes sign, this one. So the product is positive, the function is convex, right? And then here, it is concave again because the sign again becomes negative. Concave again, right? Okay. So let's say, well, this is the point of where the inflection point actually, because that's an inflection point, right? Where, well, actually there are two inflection points here. Both of these are inflection points. Okay. So we have one here and the other one somewhere here, right? So the function is concave up to here, but at 0 the function is the logarithm of 3, sorry, so it's positive, okay? So it's going to do something of this sort. It goes up here like this, like a logarithm, right? Right, it goes up here, okay? Then it becomes convex and then concave again. So pretty much something like that, right? And on the other side, it goes just like this, right? It's always concave, okay? Because here the sign is negative. I mean, once you cross this point, the 0, it becomes always negative, right? All right. Now we have to plot the two functions together and decide at which point at every interval which one is bigger and which one is smaller, because it's the minimum of the two functions what we want. And when we do this, we end up with the following plot. So here it is, right? Okay. Well, you can see here. Well, actually, there's something. Let me just comment on this. I didn't mention it, but 0 is a point where the derivative is equal to 0. So as a matter of fact, the plot that I did here is not quite correct because it has a minimum there, right? Sorry, not a minimum. It has a horizontal inflection point like this. So it looks pretty much like this. All right, and this is what it is. I mean, well plotted with a plotting program like GeoGebra or something similar. This is what the two functions look like. The first function is just like this, as we figured out. It's just two branches of the logarithm, right? Symmetrical. And this last function is It's got this branch, which is concave, and that's it. And then it's got this other branch, which has an inflection point here and another inflection point here, and then it continues like that. So it's concave, convex, concave, right? Now we plot them together, and what we want is the minimum of the function, the minimum of the function everywhere, right? And well, I can see here that this plot is not correct, because if I want the minimum, well, the minimum is correct here. This is smaller than that. Up to here, this one is smaller. Then from here, this one is smaller. But this is smaller up to here, and then here it continues like this, not like this. So this is wrong. Okay, there's a mistake in the notes, right? It should go like this. All right. So this is what the function, this, and this is what the function looks like. And there are 2 points, this one and this one, where the function exists, is continuous, but it's not differentiable because it's got 2 cusps, right? You can see that if you follow this function here, the derivative is positive. But if you follow this function here, you know that the derivative is 0. So the derivative here do not coincide of one branch or of the other. And here, well, it's pretty clear that there is a cusp at this point and it's not differentiable, right? So this is it.